And welcome to 13.3 podcast, The Nature of Solids. Again, this whole unit is about the nature of solids, liquids, and gases. We started off by talking about how the particles are very, very far apart. They do not interact with one another whatsoever, and we can predict their properties based on the kinetic molecular theory. Liquids are tightly close together because the attractive forces of these particles are very strong, but they're not strong enough to hold them in place. They're able to move around one another. The diagrams that we've used previously, if we can do it like this, is that once again gases are far apart and moving randomly, not interacting with one another. The liquids are in fact, and we'll draw it as liquid here, are in fact tightly packed together, nearly touching one another, but yet they are allowed to move around one another because they have enough energy to slightly pull away from the attractive forces that are sticking them together. Solids, on the other hand, the attractive forces are very, very strong. Okay, let's switch back to our traditional color here of our sea green. The attractive forces are so strong, in fact, that the particles are closely packed together, like in a liquid, but they are simply vibrating. I'm saying vibrated. We should say vibrating about a fixed point. The solids do not flow. They do not flow because these attractive forces do not allow them to flow. And if we draw a picture of that, the particles are going to be in a very, very orderly arrangement. And I'm just going to put excited markings around them because they are shaking back and forth ever so slightly in that fixed state. Now you can move back and forth between solids and liquids, and of course that process is melting when you're going between a solid and a liquid, and freezing is the opposite. You should know those definitions. The melting point, again, is just the temperature at which a solid, I'll put an S in parentheses, turns into a liquid. And we'll put a cursive L in parentheses, lowercase l. Alright, moving on. I think all of that should be self-explanatory. Now, about the orderly arrangement of these particles. Most solids are what we call crystals. And these crystals are sets of repeating units, and you can break these units down into very simple forms. I'm going to change my color here because that's pretty difficult to see. Let's go with a bright yellow to see if we can see that. There we go. And not all of the arrangements are in squares or cubes, but that's all we're going to be talking about here because I think it gets the point. Here's a unit cell for table salt, sodium chloride. Okay, and sodium chloride would be repeating units of this block over and over and over and over and over again. Now there are different ways that you can pack these unit cells. Scrolling down here, you can have what's called a simple cubic arrangement, where the points of your cube are simply at the corners of the cube, like so. Change colors here. Let's try it in orange. There we go. I think the yellow is being blended in there. But anyway, the points are where the atoms are going to be arranged. Now you could also have what's called a body-centered arrangement, where you still have the points, the atoms at the individual points, but then there's still room in the center of the cube for an atom to lie. Or you could also have what's called a face-centered arrangement, where, again, you have the atoms at the individual points of your cube, but then you also have room for the individual atoms to be in the face of the squares. So on this particular square here, there's an atom right in the middle of it. On this particular square here, there's an atom right in the middle of it. In the back square, there's an atom. On the side square, there's an atom. On the bottom square, there's an atom. That's just simply called a face-centered arrangement. Alright, so there are different ways that these things can be packed together. You should know the definitions of a simple cube, a body-centered, and a face-centered arrangement. That would be on the be fair game for the quiz. Now, because of this, because there are different ways that you can arrange these atoms, you have what are called allotropes, scrolling down here. And I think I overshot that. Let's bring this. There we go. An allotrope is simply two or more different arrangements. Should be two R's there. Two or more different arrangements or molecular forms of the same element. The common example to use as an allotrope is carbon. All right, and here are three allotropes of carbon. Carbon can bond in a particular way that forms a tetrahedral shape, and each tetrahedral shape is bonded to another tetrahedron, and they link in all directions with a firm covalent bond. Okay? Because of that, this is an incredibly rigid structure, and you know that diamonds are among the hardest materials on Earth. On the other hand, you can also bond these carbon atoms in discrete rings, and that's what this graphite is. All right? But each ring is only in a two-dimensional plane. It's a flat ring. And you have a series of flat rings that are lying on top of one another. And because these flat rings only loosely interact with one another, these individual rings, or sheets of rings, can slide back and forth because there's nothing really tying them together. Yes, they loosely bond together, almost like a liquid, but you can slide them back and forth, which makes graphite very slippery. All right? Graphite is black and slippery. Diamonds are clear, or they can have some color to them. That also adds to the value of the diamond, and is hard. Now, this other arrangement, which is called a fullerene or a Buckminster fullerene, or some people call them buckyballs, are simply cages of pentagons and hexagons that are linked together. This almost looks like a soccer ball. A soccer ball arrangement that gives it a lot of weird, unique properties. And in fact, a lot of the newer technologies are centered around these fullerenes or buckyballs or caged particles. Okay? But the bottom line is that different arrangements will have different properties. And because of that, we have to deal with them slightly different than other allotropes. But yet, all of these samples are simply, in this case, pure carbon. All right? So that's what an allotrope is. Just different arrangements of the same element, which obviously give rise to different properties. Now, not all solids are going to be in crystalline form. Some of them are what we call amorphous solids. So scrolling down here, an amorphous solid is a solid that lacks a repeating or an orderly arrangement. All right? A crystalline form is repeating units over and over and over again. But an amorphous solid is not that way. For example, if you look at silicon dioxide, and we should be good there. If you look at silicon dioxide, SiO2, it can exist in two forms. One is a crystalline form. It's known as quartz. This is what sand is made up of predominantly. It is a repeating pattern of silicon dioxide, and every unit is the same as the previous. As opposed to glass, glass is also silicon dioxide, but yet it is not an orderly arrangement. It's very jumbled up. It is not repeating, and so that's why we call it an amorphous solid. It has different properties from that of quartz as a crystalline solid. And we're not going to get into the details of all the different properties of an amorphous solid, but we should know the difference between a crystalline orderly pattern and an amorphous irregular pattern. That concludes 13.3 on the nature of solids. In the next podcast, 13.4, we're going to be dealing with phase changes and phase diagrams.